I'm going to talk about a subject that is relatively new, and it's going to maybe call into question some of the things that we have previously assumed or understood as not being part of physics, but maybe they are part of physics. What I'm going to be talking about is something that has happened in the past 10 years, that various research groups have created machines which simply evolve. And as they evolve, they end up solving a major problem in computer science. And the problem that they almost invariably look at is the Ising problem. I'll explain halfway through why the Ising problem is very important in computer science. Basically, if you can solve the Ising problem, you can solve all the NP-hard, those are the hardest problems in computer science. So I'll take a little digression first about some of the things I've been involved with. I was a co-founder of Luxtera, and we made silicon photonics. I think we were the first company in silicon photonics. And one of the things we like to design is we like to design photonic crystals, and that becomes quite a challenge because you never really know what geometrical structure that you might want. And so that makes it rather a challenge. But in any case, the company did succeed eventually, was purchased by Cisco, and is producing a product with a photonic crystal in it, which I'll show you what it is in the next slide. The main point of the slide is to say that you've probably used a photonic crystal today because it's in all the data centers. And if you check your email or download a web page, you're using the data center is using the photonic crystal for internal communication. This is the actual product. It is basically similar to USB connector, but instead of the speed of a USB connector, it goes somewhere between 25 and 100 gigabits per second. And it's just this connector, but you see it has a little bit of a bulge. The reason it has a bulge is that in fact, let me use my pen for the bulge. It needs a little bit of space because you convert the electrical signal to an optical signal in the yellow cable. It's just an optical fiber, and then it arrives and converts back to electricity at the other end. So it's like a very fancy USB cable. Now, the photonic crystal part serves the following function. When you do optical communication, by the time you've twisted the optical fiber around many corners, the polarization gets scrambled. So when you come and detect it, you need to separate the two polarizations and process them separately, detect them separately, and get the signal to come out that way. Now, what we end up with is not a grading coupler, but rather two grading couplers, as indicated there, and those grading couplers. And the point is that one grading coupler sends one polarization this way, and the other grading coupler sends the other polarization that way. That makes it a 2D photonic crystal, but you can see the shapes are very non-intuitive. And so that takes a lot of effort and research to solve for shape. So solving for shape is an example of an optimization problem. And I'll go through this because it's an optimization problem, but then I'll show you a much more general way to solve optimization problems. And let me go over this one and just show you an example of an optimization problem. It's a video, and what you're trying to do is simply trying to split an optical fiber into two fibers to do it with the lowest insertion loss possible. And in other words, you're trying to maximize the efficiency. And it shows you might start with something like this, but you'll end up with something like that. And what's going on here is a series of iterations in a computer program, which gradually take you to the highest, by last iteration, takes you to 99-point-something% efficiency. Actually, not quite 99, it's 98.9% efficiency. So the question is, how do you determine that this was the optimal shape to give you a low insertion loss? So this is the same picture. I have it standing still, so you can see you started with a normal ramp like this, but you ended up with something that looked rather different. So how do you determine the correct shape? So there is a method that mathematicians know about, but I haven't met too many physicists who know about this, and it's called the adjoint method. And the great value of it is let's say you have some kind of shape, like in the previous problem, you had a shape, you had a waveguide, an optical waveguide came in, and then it kind of went into that kind of a shape, and then two fibers emerged, and you had very low insertion loss. So how do you get the shape? So what you do is you do shape derivatives. It's calculus, but you'll see what the problem is. In calculus, we learn how to optimize with regard to one variable. Here we have a shape, so we have a million variables, possibly, that we would have to optimize with respect to. And you say, oh, a million variables, I might have to do a million Maxwell solutions to get this. But the mathematicians figured this out some time ago. Actually, you can get the gradient. There's this mathematical method. If I had time for another 3-4 slides, I can actually walk through the calculus with you. It's a beautiful combination of linear algebra and calculus. And so in your first calculus class, you learn to find the maximum of a function of one variable. By adding linear algebra, we can optimize a million variables all simultaneously. In other words, if we solve Maxwell's equations twice, you can calculate all derivatives at all points in space, whether you should add material, whether you should move a boundary. The gradient tells you which way to go. And this is called the adjoint method. And it's a very powerful method. So I'm going to show you, and it's a rather obvious method to do optimization in the sense that you climb the figure of merit. You just take the gradient of the figure of merit. And this is actually the gradient of the figure of merit, but it's got this complicated thing with this adjoint vector here. So I'm skipping over the mathematical part, but I'll show you probably the oldest example in optics of using the adjoint method. In making integrated circuits, the secret, of course, it's all done with photography. And so the problem is in photography, well, it didn't used to be a problem, is that you have a negative, and then you print the negative, and the positive looks just like the negative, maybe a little bigger. Okay. But what happened about 15 years ago, we started printing circuit elements that were smaller than the wavelengths. For example, here's a structure that is 55 nanometers. The wavelength is usually 193 nanometers. And so they're printing sub-wavelengths. So the question was, what shape on the negative would give you the right image on the silicon wafer? And the image is like totally non-obvious what the negative should look like, particularly when you're printing sub-wavelength. So here is an extreme example. You're trying to get this structure, which some kind of a structure on wafer, on chip, and you do the math, you turn the crank, and you get a mask or a negative that looks completely strange. I mean, you would never have guessed this in a million years. And this is the power of mathematics, is to drive you toward multidimensional optimizations. If you're talking about a two-dimensional image, there are a million things you can adjust. And so you end up with rather non-intuitive solutions. And I just remind you, in the industry, the negative or the mask is a thin film of chromium. So you're patterning a thin film of chromium. So these were probably the first metasurfaces, because it's a thin film of metal pattern to achieve certain goal. So you're simultaneously optimizing thousands of parameters, and depending upon which generation you have, you end up with all these different shapes. That gives you sort of an idea of the early uses. And this was developed in a company that I co-founded called Luminescent Technologies. But we also showed Intel how to do it. And by 2008, every microprocessor was using the adjoint method to design the photolithographic masks. it's an optimization problem, but it's an optimization problem with thousands or even a million parameters. So the point of going through these steps is to remind you that optimization is everywhere. And I gave you an example of silicon photonics optimization, a simple splitter, optimization of photolithographic masks. But throughout our lives and throughout society, there are many optimization problems. For example, artificial intelligence relies upon deep learning and something called backpropagation. So the backpropagation, it's essentially began in the year 1985, and is basically a rediscovery of the adjoint method. In fact, one of the people who just won the Turing Award is Jan LeCun, and he was a very young person at the time. And for his college education, he had become knowledgeable in control theory. Control theory is an optimization problem too, because you have to adjust all the control dials, and if it's an airplane, you have to adjust the wings and so forth to achieve a certain path. So your deviation from your chosen path is the error. So he knew that, and so he contributed this to artificial intelligence in 1985, and this led to the revolution in artificial intelligence. 25 years later, they're all using this thing, but they don't call it the adjoint method. They have a different name. They call it backpropagation, but it's the same mathematics. What you're trying to do is to adjust matrix elements so that if you do a matrix operation on a photograph, it's going to tell you what's inside the photograph. Is it an animal, and what kind of animal, and so forth. But there are so many optimization problems. Wiring a circuit, what's the best way to wire a circuit? What's the best way to pack boxes? This reminds me of before I had an SUV, I had a normal car with a trunk, and every time we went somewhere, the greatest challenge was getting all the suitcases in there, and it required trying every possibility. And that's the definition of an NP-hard problem in computer science. Is the only way to solve it is to try every possibility one by one. Protein folding is also an optimization problem. Control theory, I just mentioned, that contributed toward artificial intelligence. Computer vision, that it's an optimization problem. You have to optimize. It's the same as this is deep learning, that you optimize 1,000 or more matrix elements, so it'll project that when you operate on the photograph with the matrix, you will get an answer for what kind of animal it is. Routing, so this is very good for Amazon. So for Amazon, you have Amazon Prime, and in mechanical engineering and civil engineering, they have been doing this. You could buy software to do exactly what I'm describing. The mechanical engineers were way ahead of the optics community. Scheduling of airplanes, portfolio optimization. You want to get the maximum return, but you want it at the lowest risk, etc. So optimization is everywhere. So I gave you one example of optimization is steepest descent, but I'm going to show you that. And by the way, you do that. You have a computer that does matrix algebra, and that's all it takes. But physics gives us a better way of doing it. So what I'm going to describe in the next few slides is how physics does optimization for free. And the reason is that in physics, there are many scientific principles that are listed as minimization principles or maximization principles. For example, we have in optics the principle of least time. And the analogy is you have a lifeguard sees a drowning swimmer and will run as fast as they can on the sand because they can run faster than they can swim. But then that shortens the path in the water, and so they reach the swimmer as rapidly as possible. Well, this is the same is true for light rays, and it gives you refraction. This is the example of refraction of a light ray. You have a high-speed medium and a low-speed medium, and you get Snell's law. So that Snell's law can come from the principle of least time. The principle of least time is related to the principle of least action. If you go through the Feynman lectures, it's chapter after chapter of the principle of least action. So it's in physics, a way to do optimization. Now here's a weird one. It's another principle. This principle was presented by a famous theorist, Onsager. In 1931, he presented this idea. And the idea is that whatever physical system you have, and I put a circuit here just as an example, but he did much more general physical systems, and eventually got the Nobel Prize for this. His principle was that if you have a system that you're driving, so no way it's going to be in thermodynamic equilibrium. You're driving the system will automatically adjust itself to dissipate the least amount of power. So for example, let me give a counterexample here. And that is that you have current coming in, it's branching into two identical arms. But for some stupid reason, 2/3 of the current goes in one branch and 1/3 goes in the other branch. Well, that's not how nature works. Nature wants their identical branches, so the current should divide identically. And what Onsager put forward is that, yes, this is a principle, and you can derive the laws of electricity from it. And the principle is that this system, you'll have extra power dissipated because you have I squared R as being the power dissipated. So if you have excess current in one, it'll more than make up for the reduced current in the other, and you'll end up dissipating more power. But he, being a future Nobel laureate, he expressed it in a much more scientific way. He said that it was the least entropy production. So entropy production is not entropy. Entropy production is ds dt. Okay. So here's another principle, and this has to do with lasers, and you have many modes, and how do you know which mode is going to laze? Well, this one had slightly lower loss, and so as you turn the gain on, let me see if I can run the video again. So as you turn the gain on, it's going to laze exactly at that point and not at the nearby point here. So in this way, the action of lasing and reaching a gain threshold also tends to select for an optimization. It selects for the minimum loss mode. Okay, and by the way, in that the modes were represented on the horizontal axis. So when they shot up, there was one mode that won, and that was the point of that animation. Here's another principle in physics, the variational principle. It says that the true wave function can be compared to trial wave functions, and the true wave function will have the lowest energy in the Schrodinger's equation. So if you do a trial wave function in red, it's going to have actually excess energy when you take the expectation value of the Hamiltonian. So you can use this as a principle. Say we want to have the lowest eigenvalue, and you keep adjusting the wave function. So this is an optimization principle. In physics, it's called the variational principle. And it's a respected method in condensed matter physics and probably other places as well. Now, here's one that is like totally obvious. And that is, if you set up a system, it's going to go to the lowest energy state. So you can imagine, well, this is the lowest energy state. And if you wait long enough, it's going to end up in the lowest energy state. So that simple act of annealing is already solving an optimization problem. Now, the problem is, and this is a very universal problem, is you might get stuck. Let's see. You might get stuck in a local optimum here and have some difficulty jumping into the true optimum. And this is almost every method of solving optimization problems is subject to this risk of getting stuck in a local optimum. And in any case, it takes a long time to anneal, and you don't always end up in the perfect optimum. So, for completeness, I have one more method. This method is is used in some versions of quantum computers, and they call it quantum annealing. But in classical, it occurs also in classical physics, can be called the adiabatic method. And what it says is if you have something you can solve down here, and it gives you the ground state, and it's very easy to solve, then you turn on interactions. And once you turn on interactions, it's very hard to solve. Go ahead, please.
You said you told me when.
Sorry, sorry for interrupting.
Okay. So if you turn on interactions, it's hard to solve, but then you get avoided crossings. And these avoided crossings are all in chemistry and in all parts of classical physics. By the way, in LC circuits, you get exactly the same thing. The avoided crossing is not necessarily quantum mechanical. It occurs in the classical context. And the avoided crossing means as you turn on the interactions, you will end up solving the hard problem because you've turned on the interactions and you stay in the ground state and you've solved the hard problem. So that is, in quantum computers, that's called the quantum annealing, but I think it's this is a further elaboration of the same thing. So I've given you half a dozen physics mechanisms that will solve optimization problems, and I started by motivating that optimization problems are really important to solve in every area imaginable, and including biology, I'm sure in soft matter as well. So which one's the best? So I don't necessarily want to be the one who chooses because the choice has already been made. About 10 papers have been published in the last 10 years, or it's more than 10 groups have published papers in the last 10 years, and in which they shocked themselves by solving really hard computer science problems by simply building a machine and let the machine evolve, and it ended up evolving into a solution of the Ising problem. And I think at least 7 of the 8 or 9 of the 10, if you analyze what they did, they were actually following Onsager's principle. So Onsager's principle appears to be the physical mechanism that is most is the easiest to implement, and it's the one that people are implementing. So I will show you what all these 8 or 10 groups have done. And what I did was to analyze each system, and like some systems were optical and some systems were electrical and some systems ran at 4 degrees Kelvin, and each group is convinced that they have the only way of doing it. And I wrote a paper about 18 months ago saying, no, you're all doing the same thing. You're following Onsager's principle. So what is Onsager's principle? Often confused with the idea that entropy should be maximized. No, that's just thermodynamics. The Onsager principle says that the time derivative of entropy, the rate of increase of entropy in a system with continuous power input, that automatically becomes minimized. And I wouldn't say the Onsager principle is forgotten, but it does have a history of being controversial. Many people question it. But I will say in defense of it that Feynman liked it and gave it a half page in the Feynman lectures, which is not bad for something that's controversial. Okay, so I don't see a reason for the controversy, except that you might get stuck in a local minimum, but all the other methods get stuck in local minima sometimes too. So I'm going to give you some examples of these analog machines that provide digital answers. Just to give you an idea, the flip-flop is actually analog. It's got transistors, it's got wires and so forth. It's analog, but it's constrained to go into only 2 different states. And so you can make an analog machine. For example, here's a machine. If you have bistable elements and they're connected, let's say, with resistors. So these bistable elements will automatically give you a digital answer at the end of the day. So just like the flip-flop is a digital, binary digital machine, but it's actually built up out of real things. So it's actually analog at some level. So let me address then the problem that is almost universally solved is the Ising problem. So now we're back into physics. And the Ising problem sounds like it's a magnet problem. but you'll see it's actually much more general, is if you have a bunch of magnets and don't look at the picture, imagine the magnets are on a table, you buy a bunch of bar magnets on a table, and you want to arrange the magnets so that they are in their lowest energy state. And some of them repel and some of them attract and so forth. And that's actually a very hard problem. It's in the same category, NP hard, that you have to try every configuration, and eventually you'll find the one that has the lowest Ising energy. So you have to minimize the Ising energy. Here I've written the magnets as spins, but they don't have to be atoms. They could be classical magnets as well. So where did this come from? So it came from one of my colleagues here at Berkeley, probably the most distinguished professor at Berkeley, is Professor Richard Karp. And he noticed that the Ising problem, if you could solve the Ising, he proved if you could solve the Ising problem, you could solve 21 really hard problems in computer science. And these are the 21 problems. Of course, now we have far more of them. They're kind of listed in the graphic here. But he's in the original paper, he showed that 21 computer science problems reduced to the Ising problem. And so that's the reason why everybody wants to solve the Ising problem. And by the way, I want to entertain questions during the talk. So please just turn on your microphone and interrupt at any time. This would be a good point to interrupt because this is taking us a little outside of our comfort zone. We're into computer science here. But I've known many condensed matter physicists who perfectly understand the connection between computer science and the Ising magnet problem. So it's sort of known. And this is the original paper.
Could you give us one example which connects to the optimization of the spin configurations?
Yes, the example that is most frequently given is called the max cut problem. It's the number 21.
Mm-hmm.
Okay, and the max cut problem is very isomorphic to the Ising problem. Max cut is how do you create a boundary, the shortest possible boundary between, let's say, spin up and spin down. So it ends up, well, it's not spin up and spin down. It's just binary figures. So that's a famous one. Another one is satisfiability. Satisfiability is basically packing your trunk. Okay, how do you pack your trunk so that you can get everything in? And satisfiability reduces also to the Ising problem. And of course, it wasn't trivial. I mean, Richard Karp is a brilliant person. So each case was kind of a nice mathematical proof. But that pretty much changed the field of computer science, at least at the theoretical level. So the starting point, I'd like to just keep it concrete for the binary system, the flip-flop. The flip-flop, there are many physical examples of things that are binary that have two stable states. But if you're making an electrical circuit, it's very convenient to do it with parametric oscillators. And so the parametric oscillators, these are oscillators. Typically, you oscillate a capacitor to omega, and you get gain at omega. And the gain is phase sensitive. Let me see if I have, yes, I have it on this slide. So the stable configurations of a parametric oscillator are plus cosine and minus cosine. Those are the stable configurations. So that makes your system binary. That'll give you digital answers. And then you connect them all together. And this is sort of an extreme example of connection. In this case, it's all-to-all connectivity, which people are in awe of. It's not easy to do because you need so many wires. The blue wires are anti-ferromagnetic and the red wires are ferromagnetic. So what do we mean by that? If the two oscillators are going to oscillate in phase, you simply put the coupling resistors in parallel. But if you want to operate them out of phase, you put the coupling resistors as cross resistors. And in parallel or in phase would be ferromagnetic, and if they're cross resistors, the state is anti-ferromagnetic. So this is the analogy that we're bringing between electricity, LC circuits, and magnets. So it's bistable. Let me sort of indicate what goes on. You modulate at 2 omega, And the gain is at omega. Now, it's a little hard to see, but you can see these omega is rather closely spaced. These are rather closely spaced. And the omega ones, we just look at the blue curve. These are spaced twice as far. And what happens in a parametric amplifier, it's a phase-sensitive amplifier, so it amplifies the cosines, it de-amplifies the sines, and you just end up with cosines, and eventually they saturate at plus and minus 1. And you get this, and this is easy to implement in a circuit because there are varactor capacitors. There are varactor capacitors that will do this. Okay, and this is just a restatement that the cosines will saturate at plus or minus 1. And so now we have a mapping between what Onsager wants. Onsager wants the power, the dissipated power to be minimized. And but the problem at hand was magnets. But they both have the same optimization. You set it up that the electrical circuit optimizes it as if it were magnets, but actually you're optimizing not magnet energy, but you're optimizing the power dissipation. So let me talk about optimization a little bit more. You often have constraints. In fact, optimization is rather boring if you don't have constraints. So as soon as you have constraints, I found this graph to be very useful. I never understood Lagrange multipliers when I learned it in college. And so I have here kind of a nice explanation of Lagrange multipliers that one of my postdocs taught me. Okay, and that is, suppose you're trying to optimize the blue curve, and the optimum, and you have these contour lines, and so the optimum is right in the middle. Okay, but then you put on a constraint, and the constraint is the red curve. So you say, well, I'm trying to get as close to the big red dot as possible, but I can't get past the constraint function. So how close can I get? The closest I can come is that point. Now, that point has an interesting property, is that the constraint function is tangential to the contour lines of the merit function. And so if you take the gradient in this space, so x and y are the variables you're trying to adjust, and so it ends up, since it's tangential, the gradient of the merit function is opposite to the gradient of the constraint function. And so you have to optimize, well, you end up with optimizing both simultaneously to arrive at this point. And basically the statement that the two gradients are sort of opposite with a constant, the constant becomes the Lagrange multiplier. And so if, for example, you could stop here, but then you wouldn't be as close as if you were on the blue isocontour, blue dashed isocontour. So this is the way to understand constraints and Lagrange multipliers. But if you have any method for doing optimization, you have to have a method for handling constraints. So you'll see that comes up. Now, so what do? You have your merit function. Well, your merit function is this, it's this Lagrange function. Okay, and it's amazing how many times Lagrange appears in physics and in mathematics. But this Lagrange function that you're trying to find the extremum, what you do is use the method of steepest descent. And so you could go down to the minimum this way, or you can climb the mountain up to the optimum and that way. And so you do the gradient descent, and that's perfectly fine. We already did that when we were doing the, for example, the silicon photonics optimization or the photolithographic mask optimization. It's the most common way of doing it. So what has happened in the past few months is that DARPA has gotten very excited about this as a path that is different from quantum computing. They call it quantum-inspired classical computing, because many of the things that are claimed for quantum computing, it looks like there's a classical way of implementing it. And so they got a nice acronym out of it, QUIC, Quantum-Inspired Classical Computing. And the deadline is tomorrow, so it's a little late to get into it. but it shows that there is interest, and there are going to be quite a people. Many people have been working on this. I'm going to now give you an example of some of the people who have been working on this and the machines they have built. But psychologically speaking, each one of these people believes that what they have is totally unique, and they have the key to how things work, and nobody else has the key. So this is an example, and each one of them is successful. They should acknowledge each other, and I think they're beginning to do that. So this is very similar to what I showed you. It's not actually, well, it's similar to parametric oscillators, and they lock either at the plus cosine or minus cosine, and they have resistors coupling, and so it's pretty nice. And but you can set up a Lagrange function for it, and you want to make sure that the power dissipation is the same as the Lagrange function, so you're optimizing the right thing, and you go through it all, and it basically works. And so a careful analysis shows that the injection locked oscillators, which is what he was using, are actually following the principle of minimization generation. And the importance of the Lagrange multipliers is that there was a very important constraint, which I told you, and the constraint was you want it to be either +1 or -1. So you have to constrain the phase of the oscillators, and so that's a very common constraint. And within that constraint, you're just doing the normal optimization. So that's I like what Roy Chattery did. He's received a huge amount of attention, and well, I like it because it was just a circuit. Now here is another group in Cambridge, England. They've also had great success, but it was with Polaritons in small electromagnetic cavities, vertical cavities, if you like. And the Polaritons would couple because they're adjacent to each other. So you got your couplings, and they let it evolve and observe the phase of the light wave coming out. And some of them were positive phase, some negative phase. And so they would lock into definite phases. And oh, they could solve the Ising problem too. And they were very excited, and they published this. But I think they're beginning to realize you don't have to go to 4 degrees Kelvin. I mean, there's nothing wrong if you like to go to 4 degrees Kelvin, but there are easier ways of doing it. And indeed, it was the principle of minimization generation that they were using. And in fact, you can see there are losses in these cavities, and you're just trying to minimize the losses. So that's basically the Onsager principle. Now, here is extremely influential work by Professor Yamamoto, who I think was one of the pioneers of this because he started it more than 10 years ago. And what he had was he had optical parametric oscillators. And the optical parametric oscillators, he was very clever because maybe if you had many oscillators, they wouldn't all be identical, but he time multiplexed them into a long optical fiber. So each pulse in the fiber was a separate oscillator. And then he coupled them by tapping some power out and then re-injecting it. And so he coupled all the optical parametric oscillators and covered an optical table. And guess what? It worked. And he was also doing the principle of minimization generation if you go through it. That's kind of interesting. That's what I'm trying to get across. Here's an approach. It's not an MIT approach, but it is based on an MIT approach where you have a splitter of this type. This is sort of it's an analog matrix multiplier, but the input is optical waves, and all of these cross connects can generate. If you can adjust all the cross connects, it's equivalent to generating an arbitrary unitary matrix, coupling all the phases, and you let it go around, and then you pass it through some nonlinear element, and like a saturating element, and then you feed it back, and you do it again. And if this simply goes around, iterates many times, it'll converge on phases. Each of the fibers will have its own phase, and it's not fibers exactly, it's silicon photonic waveguides, will have its own phase. You measure the phases, and that's the answer to the Ising problem. And if you look at that very carefully, it's also the principle of Entropy Generation. In that case, it's the fiber losses that are relevant. You're trying to, because you have to dissipate the power somewhere, so it's in the fiber losses. Okay, and my group has also done something similar. It's slightly different from what Roy Chowdhury did, but very much inspired by him, using not injection locking, but simply using electrical parametric oscillators. And of course, it came out to be the same thing. Okay, so let me mention, we had a trick for doing this. So to get interesting, you need to have a large number of oscillators, and they should all be identical and so forth. But there's a simpler way to do it. There are circuit simulators that have been developed, I think 60 years ago at Berkeley. They developed a circuit simulator called SPICE. And instead of buying 32 pieces of hardware, you can just simulate the circuit, and it'll give you the same thing. So we just did the circuit simulation, but even then it was hard to do a really large number. But we did 32 and 32 magnets, if you like, and that gave you 2 to the 31 possible solutions. So to the degree that you can hardly make out the ferromagnetic and antiferromagnetic connections. And this is the minimizing. This is 32 magnets. You can solve the Ising problem by brute force. And so that's what happened. We ran it and followed it. We ran it on SPICE and followed it. The oscillators would wander around, and after about 400 nanoseconds, they would lock. I should mention our oscillators were at 1 gigahertz, and the bandwidth of the LC circuits was about 100 megahertz. And so we let it run, and after about 400 nanoseconds, the phase is locked. And so the phase is locking. Some locked at positive phase, some locked at negative phase, and then the calculation was over because very little changed after that. So the first thing, and how did we do this? We ramped up the gain from the capacitor modulation, and gradually we started 12% modulation. That gave us gain, parametric gain with 13% modulation, and then the thing took off and gave us the answer, digital answer. So, and this was sort of an indication. Some go to plus pi over 2, and some go to minus pi over 2. Okay, and that's nothing much, not much happens after 400 nanoseconds. Now, the bandwidth of the LC circuits was 100 megahertz. So if you can get a solution in, let's say, and 100 megahertz translates to 10 nanoseconds, if you can get a solution after 400 nanoseconds, it's like 40 clock periods. So this is like incredibly fast. And this is why this beats any digital computer. It's extremely fast, and also uses far less energy. So it's faster, and it uses far less energy. So this is the reason for doing it. Now, here's a chart which I kind of like, because it shows that when you run SPICE, what do you get? Well, first, before you run SPICE, you just plot every possible spin configuration or magnet configuration. So it represents a dot. And on the vertical axis, I have the Hamiltonian, or the energy, or if it's a circuit, it's the power dissipated. And you see that you have actually 33 million dots. Most of them lie on top of each other, so you don't see it. But of all the dots, the lowest one is right here. So you've done a search over 33 million solutions, and after 40 clock periods of the computer, this is exactly the one you get, which is, I would say, kind of amazing. So you solved an Ising problem of 32 spins. You solved it in 40 clock periods. So this is the motivation for doing this. Now, so I'm reiterating this point. All of these different things, the different universities, MIT, Stanford, Berkeley, Cambridge, they're all, we're claiming they're using Onsager's principle. Now here's a rather beautiful example. So this is sort of taken off, and this is a very beautiful example. These are not magnets. These are what's called ring oscillators. This is something that electrical engineers design. It's just a bunch of transistors in a loop. So eventually you have feedback and it oscillates. Now what he did, he used injection locking, which is very similar to parametric oscillation, and he let them evolve. And the amazing thing he got out of this, and this was like about, they're close to 2,000 electrical oscillators. You can do that on a chip. You can fit 2,000 ring oscillators. But what he ended up getting is the ring oscillators. There's no magnetism anywhere here, but the ring oscillators organized their phases to be those of a skyrmion, a spiral skyrmion array. So a skyrmion is a phase of magnetic thin film in which exactly this pattern, you get domains that follow exactly the spiral pattern. So I was totally impressed with that, and he was kind enough to let me have his slide. So it seems like all of these physics-based approaches, there are many of them, but they all seem to prefer the minimum entropy generation mechanism. And in effect, the physical hardware implements steepest descent physically, but produces a binary output, which is digital in the same sense that a flip-flop is digital. And the benefits are greater speed and less power dissipation. So leads to the concept of time to solution and energy to solution. And it's very powerful that way, and it gives you like amazing optimizations. So people are looking for a killer application now. I could ask what physical system will execute that application. Well, I think I've sort of indicated I'm partial to the electrical versions because those can be done on chip, and you can make, they scale because you can make a great many of the identical thing. And what is the killer app? I don't know. It might be control theory, because in control theory, you need quick response. You don't have time for a long calculation. And so that's just a guess. So that's the talk. Thank you very much for listening. We do have a paper on the subject, but I think what I've tried to share with you is that physics has a role to play in computation before we get to quantum computers. We will eventually get to quantum computers, but here is something that can work out of classical computers where we take advantage of the fact that physics already does maximization and minimization. And let's use it. Thanks very much for listening, and I look forward to some more questions.
Eli, that was very inspirational. Thank you very much. The floor is open for questions. While some of you are collecting your thoughts, a question, one of the most exciting and promising application of genuine quantum computers is, of course, factorization. Will you make some comments on whether these types of quantum-inspired computers can also perform comparatively well with factorizations, please? Well,
I have colleagues who have made that claim, but I think it's not a quantum computer. You can do optimization. Optimization is very valuable for many things, but it cannot fulfill the promise of a quantum computer. But on the other hand, I tried to indicate at the beginning that there are many forms of optimization that are very important to us. And if you need one to remember, just think of the Amazon Prime driver. He's got to deliver to 130 homes. And what is the sequence of homes that he should visit to minimize his mileage on the road? That is a problem that is a very practical problem. And I don't think you can solve it readily with a quantum computer either. So it comes up every day, and you can imagine the value to society if we could solve it. So that's the traveling salesman problem. That one reduces to the Ising problem as well. The traveling salesman problem is very famous, but it's more practical. We don't have door-to-door salesmen anymore, but we do have the Amazon Prime trucks. What is the sequence in which they should visit their customers? So that's sort of an example of one of the many things that you can do.
We should rename it the traveling Amazon driver problem.
I know
Rajiv?
it's much more appropriate for today's world.
Rajiv?
Yes, I was going to ask, so when you mentioned these optimization problems, does one need the absolute best solution, or is nearly the best solution good enough? And related to all these methods that you discussed, minimum entropy generation method, would they produce the absolute best energy for the Ising model for a large enough system?
Okay,
Or,
so that's a very
how
good.
would it scale, for example,
Yeah.
with the size of the system?
Okay, so I should mention that's a terrific question, and it depends on who you ask. Now, if you ask the people in theoretical computer science, and like Richard Karp, who came up with these 21 hard problems that were isomorphic to the Ising problem, they want the absolute best optimum. But in the real world, nobody really cares. If you can get within 1% of the absolute best, it's usually good enough. So what happened in this DARPA solicitation that I just mentioned was very interesting. The specification that they want you to achieve is achieve 99% of the best possible solution. You don't have to achieve the best possible solution. And that's how it is in the real world. There are many solutions. They cluster together toward the optimum. If you just get very close, it's maybe not that important to get the last 1%, but it depends upon who you ask. So it's very typical of these machines. They do get stuck in local optima. Okay, and then there are workarounds. Even in computer science, where they're trying to solve many of these problems, they have workarounds when you get stuck in a local optima. And those workarounds would have to be added to the Onsager machine, which is not that hard to add. But it's also, it's still no guarantee. And the reason this is hard, it's like looking for a needle in a haystack. You have 2 billion possible solutions, and we used to initially you have to check them one by one. Then you come up with better and better ways of doing it. But I'm a sort of practical person since I'm in a WE department, so getting within 1% is often very good if you can do it with very, very quickly and with very little power. And there is no other way to do these things at high speed and with very low power. So what I showed you at the beginning when we were optimizing the silicon photonics, that was not at high speed and that was not at low power. For example, the 2D grating coupler was trial and error that actually took several years to optimize. So that was before we had these mathematical tools.
Great. Piers?
Yeah, an overlapping question. In your parametric oscillator setup, did you find that it sometimes found a nearby but not minimum solution? And the related question, does the noise play the role of a kind of temperature in your machine?
Not really, but I think, well, our experience is it's very helpful to start from noise, start from a random configuration and let it lock into the desired answer. Now, the first part of your question was similar to the previous question in that, does it give you the optimum every time? No, it comes close, but it doesn't always give you the absolute optimum. And under those circumstances, if you want a better solution, there are tricks, but the tricks amount to rerunning the problem with different initial conditions. And that's where the noise is helpful, is that you get different initial conditions each time. And so yeah, that's how it's usually run. As you run it many times because it's so fast, you might as well run it many times. You start with different initial conditions each time. You get a different answer each time, or sometimes you get the same answer. But it's usually easy to check how good the answer is. You can just pick the best one.
And is it working in a similar way to finding a funnel that takes it down to the lower solution, or is it working in a different way? What's your sense?
I think
of that?
it's a physical way of doing steepest descent.
Okay.
So
Yeah.
The methods that are normally used for optimization, it always well, the ones that are really good and fast involve steepest descent. There are other methods that are really are not quite as good. The genomic method, where you try various things and then you select and then you try again. Those are they're very inefficient in the sense that you have to resolve many problems. Steepest descent is nice because it takes you directly toward the solution.
Sure.
So it tends to be very fast. And the mathematicians who've trained me in this, I've had an extremely wonderful colleague at UCLA, Stan Osher. He's a great applied mathematician, and he taught me a lot of the math behind this. While because we were the co-founders of that company that made the photolithographic masks.
Very nice.
Wow.
Okay. Thank you.
Great, Andre.
Yes, Eli. Very nice talk. Could you? So what you told us today, I'll start with a statement. Reminds me of how one could use analog machines in order to do, let's say, integration. You give a function and you could pass it through our LR circuit and get approximately the integral, right? And that's much cheaper if all you're interested is in accuracy, let's say within certain percentage. You don't want an absolute answer. And so typically the reason why historically digital machines replaced analog was because we wanted more than 99%. So I suppose the question here is one, is that really what for practical applications, that's really what desired? And as a corollary, what you described doing here in hardware reminds me a lot of how classical Ising model with random bonds is solved using Monte Carlo. One uses tricks like parallel tempering, which is really like annealing that you described, right? And there is no hope of sampling all the solutions, but you sample a lot of them. And sometimes you get stuck in a false minimum, but oftentimes you succeed and you anneal and you do it again. So fundamentally, do you see a difference in doing it in 40 clock time periods in a hardware versus doing it versus 40 equivalent operations using Monte Carlo Markov chain?
Yeah, what you're saying is very true, but analog computers have really suffered historically, and so it became kind of a problem. Now you could look at this physics-based hardware, and if you say it's an analog machine, I'll say it's consisting of bistable elements, so it's not an analog machine. But certain problems you might need to have quite a bit of precision in the resistors, and so then now you're starting to suffer some of the same problems of analog machines. So this is sort of the challenge here. Is this going to be as broadly applicable as digital computers? Well, they don't have to be, because we can pick and choose our applications, and so it's kind of a question. There is the criticism that it's claimed to be digital, but it has an analog aspect. Is that going to be a showstopper? And so we don't know. The field is still relatively young, but we are getting solutions to the Ising problem. You're not going to get this with integrators and things like that. Analog integrators. The analog computers cannot solve the Ising problem. So I think we have to wait and see what is the level of adoption that emerges. But it's very young field, and we have to anticipate what it'll be good for. So that was one of the things on the second last slide. It was, what's the low-hanging fruit? What's the preferred application? And people are still looking for that initial application, which will justify spending the money to build the chips. So just to give you an idea, it could cost tens of millions of dollars to build a chip because you have to hire all these chip designers and they demand very high pay. And you have to have a really good application to justify spending the initial $20–30 million. But once you've done that, then you could look for other applications for the chips.
Is it fair to say that what you are describing is really a quite application-specific circuit? So this is really not it's quite far from a general purpose computer.
That's right.
But the whole point is that that specific problem what you are solving has tremendous number of applications by this CARPS equivalence insights.
Yes, that's right. So we're not as general as general purpose computer, but there should be quite a few applications.
Awesome.
And these are rather important applications that we cannot solve now, like protein folding, etc.
Excellent. I'm sure that a whole lot of people who would love to have help in that direction. I'm looking at the program. I think nominally we were supposed to finish at 3. We are at like past 3:10. Rajiv and Pierce, I'm looking at you. The program says we are going to have coffee. Are we just sort of staying in this room, or
Yeah,
I brought my own coffee?
We'll take a break. I think. I think we can start again. What do you think? Would you start it? I'm losing track of what the time at 3:30. 3:30 as planned.
Yeah, 3:30 is when we have the
Round table
discussion session that Gergely will be leading.
Good. So we'll get back. We'll come back at 3:30 then. All right.
Good.
Nice to
And
see you, Eli. Thank you.
Yeah, that was
Okay,
a great talk,
thank
Eli.
Eli again for the great talk.
Yeah.
Thank you, Eli.
Great talk.